Hello all. In today's session, we will talk about the basic components of CNN. In the previous session, we have seen the architecture of CNN, where we have talked about how convolutional layers are used for extracting features of the image, and those extracted features are arranged in the form of vector called as feature vector and are given as input to the fully connected layers, which is used for classification. So let us discuss the components. The first component of CNN is convolutional layer, second is pooling layer, and the third is fully connected layer. So here the data set what we have discussed in the previous session was MNIST. The image from the same data set is used here. So this data set will classify the images into any of these classes 0 to 9, that is total 10 classes. And you can see in the image I have two convolutional layers, 24 by 24 and 8 by 8. What do you notice here is after each convolutional layer you have a pooling layer also. At the second convolutional layer you have pooling layer, and what you notice here is as I move from the first convolutional layer to the second convolutional layer, the dimensions of the image got reduced. The output here is flattened in the form of vector and is given as input to the fully connected layer to perform classification operation. And at the output, as it is multi-class classification, we are making use of softmax activation function, which will find the probability of this given image belonging to any of those 10 labels. So the text representation of this architecture is input image, perform convolution operation, apply ReLU activation function, pooling layer, second convolutional layer, apply ReLU activation function, pooling layer, output is flattened and is fed to the fully connected layer, which makes use of softmax activation function, which gives the probabilities. So let us talk about the first layer of CNN architecture, the convolutional layer, which is the core building block of convolutional neural networks. So what does convolution mean is, in mathematics, convolution is the operation of two functions to produce a third modified function. So in this context of CNN, the first image or the first function what we are talking about is the image, and the second function what we are talking about in this definition is convolutional filter, also called as kernel. Mathematical operations of these two functions are performed to generate a third modified function which is called as convolved image. You also call it as activation map, and you also call it as feature map. So these are the different names given to the output modified function what we get by performing the mathematical operation on these two functions. Now what do you notice here is the first function is nothing but the image which should be processed, and the image what is shown in the diagram is of 8 by 8 dimensions, that is 8 rows and 8 columns, and each value in the box represents the pixel values of that particular image. The second function what we are talking about in the definition is convolutional filter, and the filter what we are using here is of 3 by 3 size. Anyways, the size of these filters will be discussed in the next slides. In this example, I am using a 3 by 3 filter with pixel values, and the output convolved image what you get is I am placing this kernel or filter onto the image here, performing the dot product, that is convolutional operation of the corresponding boxes -1 into 3 plus 0 into 0 plus 1 into 1 plus -2 into 2, so on, and the output what I get is -3. So -3 is the new pixel value or the destination pixel value of this convolved image which is in the matrix form. So what is filter? This filter will slide on the image one step after the other to generate new destination pixel values of convolved image or activation map or feature map. So what you notice in the diagram is I am using a 3 by 3 matrix in the middle, which is a convolutional filter, also called as kernel. This kernel will slide over the original image pixel by pixel, does some mathematical calculations to get the new convolved image on the next layer. Now what if I paste, for example, we talk about this parameter also in the next slides. Stride is equal to 1. What does that mean is step size, I can say. If step size is equal to 1, if I mention step size as 1, then to get the new pixel value of the next box here, I need to place this slide on the taking step size as 1. I will shift my filter one step towards the right and slide onto this image. So I'll perform the convolution of 0 into -1 plus 1 into 0 plus 5 into 1 plus 6 into -2 and so on, so that I'll get the new destination pixel value of this convolved image. So in this way, this filter will be sliding on this image one step after the other. Why one step? Because I have mentioned the step size as 1. It will move and generate the new pixel values. So I am performing mathematical operation of two functions to generate a third modified function called as the convolved image. This is called as convolution. Anyways, we will look into these mathematical calculations into deeper in the next slides. Now what is this area? This blue box is formed by placing the filter onto this image, and this point, this area is called as the receptive field. The area of the image that the filter convolves is called as the receptive field. Earlier, this was my receptive field where I got -3 value. With step size as 1, I have shifted one step towards the right. This will be my next receptive field and so on. So the area of the image that the filter convolves is called as receptive field. So this is the example. These are the receptive fields where the filter will convolve onto the image, sliding one step after the other to generate the output. Now what are these kernel values? In this I have used some kernel values. Anyways, these are the pixel values of the image given. But these kernel values, how do we get is, in MLP we have discussed about weights. And how did we use those weights value? Those were randomly initialized. That is, either we have taken W is equal to 0, 1 and so on. Similarly, these are also randomly initialized values of the filter. That is, we need to randomly select some values which are called as the pixel values in the filter. So the max behind MLP is y is equal to W1x1 plus W2x2 plus W3x3. The same max will be used here. When I have three inputs x1, x2 and x3, I get the output y. Let W1 be the corresponding weight here, W2 and this is W3. This W1, W2, W3 are nothing but the filter values or the pixel values of the filter multiplied by the input feature. This input feature is nothing but what? The pixel values of the image, and W1, W2, W3 represents what? The pixel values of the kernel filter. How did I get W1 value? By multiplying W1x1. That is, by multiplying, we have behind 93 pixel value of the image multiplied by -1. Then I have 139 multiplied by 0. Then I have 101 multiplied by 1 and so on. And the resultant value of the new pixel is 243. So the same mathematical operation or mathematics is involved behind MLP and CNN. That is, weights are nothing but the pixel values of the filter or kernel, and x1, x2 inputs are nothing but the pixel values of the image The only difference between MLP and CNN is in CNN, these values are arranged in the form of matrix. So to understand how the convolution operation happens, let us look into the image here. This image shows the convolutional calculations in one area of the image to compute the value of one pixel. So what will I do? These are the pixel values of this image what we are highlighted in here, what we have highlighted here. Now I have used the convolutional filter of 3 by 3. I will place this filter onto this and perform the mathematical operation of dot product. So 120 into 0 plus 140 into minus 1 and so on. I got the value as 60. So this 60 which is greater than 0 represents that a small edge has been detected. So this filter is used for what? Detecting the edge of this particular part of the image. So each convolutional layer contains one or more convolutional filters. This is called as convolutional filter. So one convolutional layer may have many number of convolutional filters. This number of filters in each convolutional layer will determine the depth of the that convolutional layer. Because for example, I have hidden layer. If I am using 3 nodes in the hidden layer, and if I increase the number of nodes in the hidden layer, this is same as increasing the filters in the convolutional layer. This hidden layer is related to MLP model, whereas this kernel is related to CNN model. Now let us see how this convolutional operation occurs in Keras. So from Keras, I will import the convolutional 2D operation which will perform the convolutional operation. And this is the syntax where I will use these 5 hyperparameters. You have filters, you have kernel size, strides, padding and activation. Anyways, we have seen that it is recommended to use ReLU activation function in neural networks. So it is mentioned here as ReLU activation function. Anyways, we have studied about these activation functions. Let us talk about these 4 hyperparameters. And these hyperparameters are the parameters which we can either increase or decrease. So let us talk about these hyperparameters. The first hyperparameter is filter, which we have already discussed. This filter is used to slide one after the other onto the image to generate a convolved image. And kernel size represents the size of the filter what you are using. It can be 2 by 2, 3 by 3 or 5 by 5. Stride represents the step size what you are using to slide the kernel on the image. And we will talk about the 4th hyperparameter, that is nothing but padding. So the first hyperparameter is filter, which is also called as kernel. And it is a small matrix which is same as that of the weight used in MLP model. So in MLP model, weights would tell the importance of the input feature x1, x2 and x3. Similarly, these pixel values also tell the importance of those pixel value of the image. So this is the MLP model, how the neurons are stacked one over the other in hidden layers. Same is the case here. We have convolutional layers and we have these hidden layers are replaced by convolutional layers in CNN. And to increase the number of neurons in the hidden layers, we will increase the number of kernels in the convolutional layers, and each kernel unit is considered as a neuron. For example, if I have a 3 by 3 kernel in the convolutional layer, that means I will have 9 units in the convolutional layer. If I have 2 3 by 3 kernels, then I will have 18 units and so on. So increasing the number of filters will increase the depth of our convolutional neural network, but it will make the network more complex. We'll talk about the next hyperparameter called as the kernel size. So it controls the size of the receptive field. So the other name for kernel is convolutional filter. It is matrix of weights that slides over the image to extract the features. The kernel size refers to the dimension of the convolutional filter, and generally we make use of 2 by 2, 3 by 3 and 5 by 5. But the intuition is that the smaller filters will capture very fine details of the image and bigger filters will miss the minute details of the image. So most of the time we make use of the small size of the filter, that is 2 by 2. Bigger the kernel size, deeper the network, which means that better it learns. And however, it will increase the computational complexity also. Coming to the next parameter, which is stride, it is nothing but the step size, and the parameter, the relationship what you generate, the output size is input size minus kernel size by stride plus 1. So we can have step size as 1, we can have step size as 2 and 3 also. And this is the formula to calculate the output size of the convolved feature. When you have size of the image, when you have kernel size and stride size, it will generate the size of the output image. So anyways, the remaining we will do it in the next session. Thank you.